Good afternoon. This is Dr. Heidelberg, and this presentation will deal with motor and encoder sizing. We are in Module 7 of the course. We get to the Module 7 reference material, click on PDF motor encoder sizing. This presentation will cover a few topics. As we see over here, we will discuss the different driving devices in automation, and we look at the motor and encoder in robotic application. We'll see the principle of operation, the construction, some of the specification, and also we'll look at one of probably most common jobs that young engineers do when they get into the automation business is they start with quite a few applications where motor and encoder as well as actuators and grippers have to be sized. This discussion will focus on motors and encoders. Looking at the different driving device options, there are traditional hydraulic and pneumatics, which are simple in structures and competitive in price, yet they have low accuracy and may require additional peripheral equipment and that may add to noise as well as environmental pollution. We have on the electromechanical devices stepper motors, which are competitive in price, small in size. Yes, yet they provide vibrations and may slip pulses and have lower accuracy. They're typically not working with feedback encoder, and they also induce some audible noise. Induction motors also competitive price, and they have low precision as a weak point. The ones that we will focus on primarily are servo motors in this discussion. They have high precision, they have high driving force, could be large size, they have slight noise and vibration, and excellent maintenance and environmental proof, and comparatively they have a higher price. Linear motors are also high performance. They are being used extensively in Cartesian robots, and they also have relative high price. These references are taken from what we see over here, the internet documents. We thank all the contributors, and we encourage the students to click on them and take a look at the more specific details. The picture that we look at now demonstrate the way various feedback devices, sensors, and motors are being used in the robotic process. We see over here a robot which is working in tandem with a conveyor belt. There are parts over here on the conveyor belt. There are sensors that detect the parts. The sensor sends to the PLC a command that the part arrives. The PLC sends a command to the robot to pick it up, and so on and so forth. Over here we see the schematic. A motor is driving a conveyor belt, and we have a sensor over here attached to the base of the conveyor belt. The senses boxes which are coming in. We will do in our final project at the course some processes that uses the PLC, the robot, and the belt in very similar configuration. We may have sensing devices on a gripper that sense the forces, not to slam the packages with damaging force. We may also have a sensing device fixed to the frame or the inertial frame to provide object recognition or increased absolute accuracy. They all fell back into the PLC that orchestrates this entire process. The feedback is coming into the PLC, into the I/O input-output box, and it gets the signal to the motor to stop through the field bus. For the robot, we see that a typical link here is a servo motor that receives power from a servo amplifier, and the servo amplifier in turn receives a command, a low power command for the position controller. In the back of the motor there is a feedback device, an encoder that feeds back the actual position. The PLC or the trajectory generator in a controller puts the desired position. There is a difference between the desired position and the actual position, which is defined as the error, and the controller filters are acting on the error, on a derivative over the error and an integral of the error to command the servo amplifier. So this shows us how the overall system uses motors and feedback devices. The electrical system is typically packaged in a electrical cabinet, which includes the servo motors, the power supplies, the HMI, and the EMO, all in one package. It could be in turn on a panel mount device. This shows us different ways that motors and encoders are connected to peripheral equipment. Here's a rack and pinion device. The gear is making that rack to move back and forth. It's being driven by a motor and an encoder at the back. This is an indexing table that has a belt-driven device and a motor and encoder that is driving it. Here's another example, so-called belt-actuated linear stage. Many companies such as Festo and Parker Hannifin are manufacturing these standard stages. They include a slide, they include a base with two pulleys and a motor and encoder that drive them. Here's another example, commonly used actuator, which is called ball screw or lead screw stage that has a slide, a ball screw and lead screw mounted to the base, and a motor and actuator that drive it. Here's another example of a friction device that drives a material such as paper. And over here is another configuration, more complex. It shows the motor driving friction drive with different markers that determine the arrival of the product. The very basic principle of motor operation is the so-called Lorentz force law. We have various variables over here. One is a magnetic flux, and it can be generated by induction or by a magnet, by a rare earth magnet or a regular magnet. There is a coil over here, or conductor, which is part of the coil, which conducts current, which is designated as I. And according to the right-hand rule, the cross product of vector I and vector B, which is the flux, I is measured in amps. The flux is measured in Tesla. Tesla is, by the way, 10,000 Gauss. Sometimes it is measured in Gauss. And if this is in Tesla and this is in amp, the net result, the cross product of these two vectors will give us the direction of the force. And the force will be in Newton when I cross B is multiplied times the length of the conductor. Now, to apply this to motors, we see over here we have a brush type schematic diagram where the positive voltage is coming into this brush and the negative is coming to this brush, and the current is flowing through the conductor from the positive to the negative. So according to the Lorentz force law, if we have current moving in this direction and we have flux going from the north pole of the magnet to the south pole in this direction, then the cross product will be in this direction. This is the force acting on this coil, and then the torque that will be generated by this motor on a shaft, motor shaft, will be, according to the Lorentz force law, I times L, the length, times the flux, times the lever arm, which is half the width of the coil, and it also has to be multiplied times sine theta. Sine theta is the complement of alpha, the angle of rotation of this particular coil. So the complement will be in this direction, and the lever arm will be the L times sine theta, will be the lever arm from here to here. So this is one side, it has to be multiplied by the second side, and the total sum gives us the torque of this motor. So that's a basic principle. This being applied to various types of motors, and we'll see in a minute. Some of them are brushless AC motors. These are the ones that we will focus on. In this example, we have magnets on a rotor, and then we have the coils, the winding on a stator and the current into the coils in order to generate the force with the magnetic flux is being commutated through the phases. It's called U, V, and W phases. The phases are being detected by the position of the rotor with Hall effects that sense the magnetic flux. We have an induction motor over here where instead of magnets we see that the rotor has an induced magnetic flux that goes through the iron core into the coils on a stator, and the net effect is still the torque as we saw earlier. Similarly, we have stepper motors where the stator has an induced magnetic flux, and we may have the switched reluctance magnet or the actual magnets on a rotor, and as we switch, for example, this pole or this phase to the north pole, if this is the south, it will be repelled and will move into the one direction, and then as we switch this one, it will be either attracted or repelled accordingly. And the stepper motors will, in each one that we switch the flux, will make one step. The way the motors, industrial motors, look like are seen over here. That's the way the servo motors look like, and many of them come with plug-and-play connectors, mounting holes for the motor to be mounted to the system, and then one plug is for the commutation of the current, and another one is for the feedback device. We have two basic type of motors, DC servo motors and AC servo motors. We'll see how each one is being constructed. This is a typical DC servo motor. We see that we have the stator, which is a fixed element, and then we have the mounting bracket, which is fixed to the stator with the mounting holes to the mounting bracket, which attaches the motor into the robot arm. Then the rotor is mounted inside the stator along its shaft. This is the shaft, and it has a ball bearing on each one of its sides, and it has a commutating ring over here where the brushes come into contact. Over here we have the brush assembly where the plus and minus brushes are being mounted to. These are the weakest element of the brushed type motor. They were the quickest when we talk about brushless. Then the bearing of these mounting mounted on a shaft are the weakest element that determine the life. Then we have an option of having a brake for the motor and also a tacho generator that feeds back to the controller the velocity of the rotor, as well as an encoder that feeds back the position of an encoder. And in some cases we also have a gearbox all mounted as an option. This is a way that the AC synchronous motor is looked. It's usually of long and low profile to reduce the inertia and allow high performance. Many times these are sensitive surfaces which have to be protected when they are shipped to customer. Here's an example of an induction motor, and again they are phased energized by Hall effect. They are brushless, they don't have any magnets, and they induce the current inside the motors. Before we look at the differences between the different motors, let's take a look at the way an AC servo motor is being constructed. We see that we have a long shaft with magnet mounted on a shaft, and then we have the winding of the coils in the stator. And the shaft over here has the ball bearings and also seals to provide the ingress protection. The frame over here comes in various size, and it has an encoder in the back. The difference between the different type of motors is listed on this table. We have both motor and drive that usually come together by the manufacturer. And if you look at the induction motor, it's the design is simple. The stator is a coil and the rotor is a coil. Feedback is an option. The speed is about 3,600 RPM. The range of power is extremely high. This is the winner of all of them in the power. And the bearing is the limiting factor of its life. You see that the speed control accuracy is 1:200. So if we move in a certain RPM, then 1/200 of them will be the way we can control it. And then the frequency response, the bandwidth is about 30 hertz. We can produce 150% of the rated force torque as a peak torque, and it has a position accuracy very close, so plus or minus 10 millimeters. The DC servo is complicated. It has permanent magnet on a stator. It has a coil on the rotor, as we saw. It has an encoder with 3,000 RPM. It has a range up to 3 kilowatts. And the brush life is the limiting factor of the motor life. It has a ratio of 1:1000 of the speed control. Frequency is 100 hertz. Maximum torque is 300%, and the accuracy is about plus or minus 10 microns. The AC servo motors, which is the high performance, which is typically used in robots, has an intermediate complexity. It has a stator with a coil, permanent magnet on the rotor. It has an encoder feedback. It has up to 5,000 RPM, 22 kilowatts power, and it is limited by its bearing lifetime. It has speed, position, and torque control, and it's the winner as far as precision, and it has a very high bandwidth. It can go up to 300 of the maximum torque in terms of the supplied current. It takes about 1 second to burn a hot coil if we run over 300, if we run at 300% rating within 1 second. Typically, at this rate, all the acceleration, deceleration happens within a few milliseconds, or 10 milliseconds, which is way below the limiting factor of 1 second. And the position accuracy is on the order of micron, which again, it's very high performance, very high speed, very high precision, both dynamic and static. The induction motor is simple. It has a stator and rotor with coils, and it has a winning element in the RPM. It could run 20,000 RPM. It has a high kilowatt rating and has relatively good speed control and also bandwidth of about 100 hertz. And the accuracy is on the order of 20 microns. So this is the pros and cons of the various motors. Here's another example that shows us how the bearings, which is the limiting factor in AC motors, are being connected between the stator with the coils and the rotor with the magnet. Many times we have seals over here to provide protection against dust and fluid. The coils and the magnets come in various densities and shape. The more density we put on a coil, then we have, of course, higher power. And with the shape of the magnets, you see that the magnets may take various shapes, not necessarily sharp edges. And that is done in order to reduce the so-called cagging disturbance, where the magnets of the core hit the lamination, which are steel slats for the winding, and generate a shock. So to attenuate the shock and reduce this impact, then these magnets get various smooth shapes. This is an older version of a robotic course that shows how the motors are related in terms of speed and torque. We see that as the torque of the motor increase, then the speed of the motor decrease. And we see over here, this is the speed, and this shows the current and the torque. As one is increasing, the other one is decreasing. We can choose motors with various combination of maximum torque and maximum speed. One factor which is the same is the power. The power is the product of force and or torque and speed, and therefore when the power is constant, when one is coming down, the other one may come up. Here we see an example of a stepper motor, as we saw earlier. This is a switch reluctance so-called stepper motor. So when we excite over here the poles, then the teeth of the stepper motor will line up such that the magnetic flux will have minimum energy. And that is when this slot exactly lines up with this notch. That's why it's called switch reluctance. It's used extensively, not only in rotary steppers, but also in linear stepper. A company like Universal, which makes its flagship of SMT assembly machines, using extensively the switch reluctance linear motors. Over here we see a typical example of a motor manufacturer that provides us a description of all its motor range, the feedback devices, whether it's serial, analog, or digital or incremental or magnetic device, whether it's analog or digital. Typically, they are integrated within the motor, and the manufacturer will give us the details. Many times we may need to provide an external encoder, and we see some manufacturers of these devices. And then we, of course, we have the power supplies, the phasers, the AC input voltage, which they may run with, and the various applications that they are typically being used for. As far as the encoders, we will talk about various types of encoders. We'll start with the optical encoder. The basic principle is that we have a disc which is slotted, and it's mounted on a rotor of the motor. Then we have on a body of the motor, we have light emitting elements which go through the slots. They conditioned, and then they hit a light absorbing element, and in turn they provide a series of pulses, and these pulses typically come in separated at 90 degrees. You see over here, and one of them is describing the position of an index position, which is a reference for homing or to start counting these pulses. So see over here 3 of them, and then we see another 3 which are redundant in order to provide reliable counting. Similarly, we have the possibility for using these devices to commutate the servo amplifier in order to provide the currents at the right timing to the coils. Here's another example taken from the old description of the MET 415 robotic course that shows the slotted disc connected to the motor with a light source, and then a detector going into the computer to make the counting. Here's an example of how the encoder may change the analog signals into digital signals. So when the light is hitting this slot, it will be indicated, for example, as binary code 1 or 0. And when it is having dark, like in this position, it will also indicate 0 and 1 depending how the manufacturer decides. Now, in this particular example, we see that in this position we have the outer element is detecting light, and the lower detector is showing dark. As we move clockwise, we'll see light and light, then we'll see dark and light, and then we see dark and dark. And then if we assign 0 to light and 1 to dark, then we'll come with the binary codes that can allow the robot, when we do homing, for example, to find out the direction of motion, and also to count the number of pulses. And if each pulse has a certain degree, like we see over here is maybe 5 degrees, then each one we switch from this binary code to this binary code, we add up so many degrees, and that's the way the encoder counts its rotor position. Here's another example that shows the specific encoder we use on a scorebot that we have in a lab. We see here the slotted disc, and we see over here the LED separated at 90 degrees, and also over here the photosensor separated in 90 degrees. So this element is attached to the rotor with a screw over here, and this is attached to the stator. We see here an example of a magnetic encoder where the rotor has magnets and all the Hall sensors are provided on a periphery, and this is a typical technical specifications of a rotary encoder. It tells us how many bits the encoder provides. It tells us what's the maximum RPM, the repeatability, which is the two least significant figure over here, and also telling us what's the setup time, what is the over here we see the format that the signals are being transmitted is 422. How many volts it takes? It takes 5 volts to run this encoder and 100 milliamp. It also gives us the different options of encoder size and the size of the diameter. Also gives us the mass in order to determine the inertia which is added to the rotor, the temperature condition, the humidity, environmental condition, and the magnetic flux which it interferes with the environment. These are typical specifications that we have to understand before we apply any of these encoders. This is an example of an induction encoder, a high resolution encoder that is typically used in high velocity application, and it tells us that this particular encoder can run up to on the order of 100,000 cycles per revolution. It has, of course, the advantage, like many other encoders, that it is totally non-contact. A different type of feedback device, which is used in harsh environmental conditions, like in outdoor equipment, is so-called the resolver. The resolver is using a induced voltage in order to generate sine and cosine waves per one cycle, and then it can be resolved into its quadrature, and further by using logic multiplier in order to determine the position of the device. Here's another example of a high-resolution encoder produced by a company called Renishaw. We see over here a read head and high-resolution grading on the peripheral of the ring, which provides very high resolution on the order of nanometers resolution, as well as very, very high accuracy. Similarly, the same company is providing linear encoders, high performance on the order of 2 nanometers, and we have again a read head and a long scale along the Cartesian or prismatic link of a automated equipment or a robot. The resolution of the logic multiplier can be amplified with the logic multiplier. We see a company over here that is specialized in motor controllers and amplifiers for robotics and positioning system. It's ACS motion controller, now owned by PI, and we see over here that we have various options for multiplication of the basic resolution, and that is depending on the frequency of encoder pulse transmission. We see over here how the typical logic multiplier may be connected to an encoder through these connectors into the controller. So we come in with a low resolution device, and we could amplify it up to a factor of 2000 in this particular example, and get higher resolution. Over here we have several definitions using encoder terminology, and we recommend that the student look at it and study it and try to become familiar, because these are often used in industry in terms of defining the properties of an encoder. What we'll do in this part is we will take a look at one of the more common applications for a automation engineer, and that is a sizing of motors, encoders, actuators, and grippers. And we'll focus on sizing here. We'll see an example of sizing an actuator and a motor and an encoder as an example. So it is important to remember that 50% of the solution is based on our understanding of a need. We have to understand the need, then we have to configure a proposed solution to the need, conduct a system analysis, and then go through actuator sizing, motor sizing, encoder sizing, and then many times also gripper sizing, and also the frame sizing. In this particular example, we see a customer that is interested in manufacturing a dispensing device. We have the dispenser over here, and the customer is interested is using standard actuators in a gantry configuration, and the actuator that the customer in this particular example decided to use is those of Parker Hannifin. This is the web link where we can find all the information related to this manufacturer. So we have here the specification of the kinematics. The travel is 2 meters long on the X direction, 1 meter long on the Y direction, and 200 millimeters on the Z direction. Plus we have a rotational on a yaw of 300 degrees, and then the pitch is going to be fixed for the application. We also have specification of the weight of the dispensing head, and we also have the offset over here, which is important to calculate the AB arrow between the mounting location of the dispensing head and the point of interest, which is the nozzle. With that said, we could continue here with the other forms of the specification, such as the maximum linear velocity, which is requirement for this particular dispensing device, maximum allowable acceleration for proper dispensing, and also the rotational acceleration are all specified. The duty cycle, which represents what is the percentage of time that the machine is actually under loads versus under a stationary or constant velocity with minimum load, is also defined over here as 30%. And then the repeatability, which is required over here, is also specified as 0.5 millimeters. Now, with that given to us, we could start by looking at the allocation of the allowable repeatability to the various sources. We have to understand that the repeatability at the point of interest, which is specified as 0.5 millimeter, is a contribution of the repeatability of the x-axis, y-axis, z-axis, and r-axis. So if we allocate a certain budget, and this is typically done by an experienced engineer, and it takes quite an experience to come up with these numbers to start with. These, by common sense, will be such that when the AB offset is largest, as from the x-axis to the point of interest, we will give it more of a budget. And when we close to the point of interest with the nozzle, we'll give it less of the budget. So this is a common sense type of allocation. Also, when we add up algebraically all of these numbers, we come up with 0.5 millimeters. But we know that the repeatability is a statistical error, and the total error of the sum of all of these contributions will be, according to the statistical laws, the square root of the squares of each one of the standard deviations. And when we go through that calculation, we find out that the expected standard deviation or the repeatability at the point of interest will be not the algebraic sum of all of these contributions, but rather the statistical sum, which is about half as much. So if we give this error budget, we have a safety margin as expected. We can also organize our information in a nice diagram that shows all the components with all the various definitions for them, and then summarizing all the specifications in a nice table. So rather than going to the customer specification, we can actually make our work a little bit more organized by summarizing all of it in a nicely organized table. Coming down on the analysis, we see over here that not only that each one of the components has to be budgeted, but for the rotary, for example, we have to realize that there are several contributions. We have the AB offset, which with the wobble will cause an error, and we have to budget it. And also we have the encoder of the rotary stage with its AB offset is going to cause another error. And then we have to statistically combine these two errors. So if the budget of the total rotary error is 50 microns, then what we could do is we could provide the rotational repeatability of the encoder, a budget of 5 microns. The radial runout, we can provide it 20 micron, and the wobble effect at 200 millimeters, we can give that as 25 microns. And once we decide on 25 microns as a budget, then we can calculate what would be the requirement of the rotary stage in terms of wobble, and we simply take that budget of 25 micron, divide by the AB offset, and we find the angle over here as 26 arcsecond. So when we choose the rotary stage with these assumptions, we better be at 26 arcseconds. Many times we cannot find a rotary stage like this. Then we have to go back and iterate on our assumptions and try to ease up on the requirements with a trade-off with other devices, and try to hit the bullseyes with another iteration. Once again, we summarize all the information in a nice format, and then we can start calculating with this information the required motor torque by using a certain safety factor, a safety factor of 2, very common in mechanical engineering, to make up for many assumptions or many unknown effects. And if we multiply the inertia of the rotary stage and the nozzle times the angular acceleration times the safety factor, we can come up with the torque required by the motor for the rotary stage is 3.77 Newton meter. We need that when we size the motor. And then we also have to consider other effects such that the centrifugal and radial effects, which will act on a motor and the manufacturer will give us the capability of the motor to withstand these forces, and we have to be ready to understand what is the axial force that the motor can take and what is the radial force that the motor can take in order to size them properly. Once we have all this information, we can go to the catalog of the stage. In this particular case, Parker Hannifin Data Corporation in Pittsburgh provides us this information, and we can go to their catalog. We can click on that. I recommend that the students will do that in order to see the details, find out the smaller stage, which most likely is going to be the lowest cost, that will meet all the requirements, and try to size it up. Over here we see an example where we summarize all the requirements over here, and we find a stage, so-called R100M over here in these specifications. And we see over here 100M, which is the smallest one, and we compare the selected stage specification with the required, so we're making sure that each and every one of them is being satisfied. Once we select the stage, we can now find out what is the weight of the stage, and also what is the torque and velocity in order to size the motor, which will be connected to that particular stage on one hand, and also to use this weight as we go into the sizing of the next stage, which is this stage which connected. To summarize these requirements, we see that for the Z stage, we have this table with the moving weight estimates of dispensing head, which was given to us, and the rotary stage that we just found and sized. Plus, we always want to keep in mind that there are brackets and cables and motors that we did not size yet, that we want to estimate their weight, and we come up with a total 17 kilogram estimated moving weight for the Z stage. We go to the catalog, and we choose the smaller size stage that we feel will meet the specification. We see over here that the maximum travel of the 400 series XR seems to be suitable, so we could click on that link and go down and see the details of this stage. We see how the stage looks like, and then we find out the stage that meets the requirement. So if we required 183 newtons axial force, and we're given here 34.2 kilogram, which is 340 some newtons, then we know that this stage is going to satisfy the requirement. We also check the repeatability of the stage, and we required plus or minus 100 microns, and the stage provides us plus or minus 12 microns. Also, the duty cycles seem to be suitable. So we have here a conclusion of what is the stage that we are selecting, and we can further down go through the details and find which particular lead we like to use on a ball screw. We have two options, 5 millimeter or 10 millimeters. Once we choose this size, and we know what is the maximum revolution per second that the stage could provide, we know with the pitch what is the velocity that we can provide, and we can check it with the requirements, and it also gives us, multiply that times 60, the RPM that the motor has to provide. So we see over here that the torque of a motor is 0.8 Newton meter, and because it's a ball screw, it has a lot of mechanical advantage, and the RPM for the motor has to be 1200, and the required resolution of the stage is 2 microns. When we do the motor sizing, again, we summarize the peak requirements. We can use this formulation that relates the duty cycle, the peak requirement, and the continuous requirement in order to determine the continuous torque. And once we have the continuous torque and the peak torque with the RPM, we can go down to the torque speed curve of the motor and select the motor. Once again, we go to the catalog of Parker and Hannifin that provides also options for the motor, so it's a one-stop shop. And we choose the motor that seems to be good for the application. Since we do dispensing, we'll choose a slotless motor for high smoothness of motion, and then we'll go down the specification to size the motor. So over here we see the motor that we like to choose. Over here are the detailed specification of the motor with the stall current, the peak current, the stall torque, and the power. All of these are being given to us. We primarily focused here on the peak torque, continuous torque, and the RPM. And depending on the different winding, we can switch the torque and the RPM as we saw earlier, and select the motor both for the rotary, it happens to be SM161A, and for the Z-Stage SM160A. And we could make sure that these requirements meet the motor specification by going to the torque speed curve and making sure that the operating point for the continuous torque and the peak torque are both below the selected motor size continuous line and peak line. This point is the peak torque has to be less than the rated peak torque, and this point is continuous point has to be on or less the rated torque. Now, since we have a factor of safety of 2, we are good at this location. Then we come into the encoder sizing, and we recall that we call 1 arcsecond repeatability for the rotary stage and 2 micron for the Z stage. Since we have a gear ratio of 60, we could reduce the arcsecond from 1 to 60 arcsecond, and then if the repeatability is 60 arcsecond, then the required resolution should be 10 times better, which is 6 arcsecond. So the required encoder count per revolution will be, we can calculate that at 216,000 counts per revolution for the rotary. For the Z stage, we can go through the same process and find out that we need 2,500 counts per revolution. So if the standard provided encoder at the end of a motor is 1,000 resolution, for the rotary we would need 256 in order to come up with 216,000, and with the same encoder resolution, we would need a logic multiplier of 32 in order to come up with 2,500. The diagram of the encoder with all the options are given to us by the manufacturer over here, and finally, when we want to order the part, we go to the part numbering system, and this allows us to choose from all the variables that we size the motor designation, the type definition, the winding, the feedback device, the shafting mounting, whether it's flat or slotted, and also the cable length that we want to provide for the encoder and the motor, and also the type of gearbox, if that is what we choose to add to our configuration. This concludes our presentation of motor and encoder sizing, and we'll do more of it in upcoming exercises and lab experiments. Thank you.